that you come to basic expressions like these regarding sequences and series, and you can imagine. So you don't have to write out what I'm about to write out. You can just imagine it, and then and sometimes you'll write it out, but you need to have the right mental image of these things when they become part of larger, harder problems. Okay? So n factorial means start with n, then you're going to multiply down. Each factor is 1 less than the previous factor until you reach where? All the way down to 1. So it would be n minus 1, n minus 2. Keep going like that until you get to 1. You got to be solid with factorials. When you see factorial, you think this. When you see n factorial, you think what I just wrote without having to write it. So it's just automatic. Okay? Let's go down and do this third one next. What does negative 5 to the n mean mathematically? What are we doing mathematically that equals negative 5 to the n? Well, we're multiplying what together? Lots of negative 5s. How many? N number of times. N negative 5s. Somehow in what you wrote has to express that you're taking negative 5 and you're multiplying it by itself n times. N negative 5s multiplied together. Okay, let's do this sequence down here next. What is a sequence? A sequence is a list. It's a list, an ordered list. So the first term is going to be what in the list? 2/7, right? When n equals 1. When n equals 2, what do we get? 4 over 13. When n is 3, 6 over 19. So as long as you put 3 or 4 or 5, there's no kind of rule for how many. But when does it start? When does it end? So 4 would be 8 over 25. How many terms are there? Okay, so I don't want to answer a lot of grading questions. Like, if I did this, would I get it right? But go ahead.
My question is like, could you also write it out like 2n over 6n plus 1 and like 2n plus 1 over 6n?
That's not what it is. That's not what that. It's not what that means. Then you're just writing. That's a new sequence. 2n plus 1 over 6n plus 1 plus 1. That's a different sequence. The sequence means when n equals 1, you get the first term. When n equals 2, you get the second term. So that's not the same.
But can't you evaluate the sequence from like random numbers?
No. The sequence means you start with n equals 1 and you get a term, and then you have n equals 2 and you get the next term. So no, it doesn't mean that. Questions on that one? Okay, and then what is this? So what does this mean? It means add all that, add the list, add every term in the list together. So this skill, so to be able to write it out is important, and then eventually when things get difficult, just like I said, you just look at it and you think that. So you when you see something there on the left, you automatically think whatever it's equal to on the right. That's going to be crucial, because if you're just trying to memorize rules and I put this here and you don't have these meanings, it eventually will catch up to you, and you'll start having a difficult time.
So the infinity is saying that we're going up to n equals infinity, and that's the same thing that the dot 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 is expressing.
Sure, right. So this means we're just going to keep adding terms without limit. And if you put dot dot dot, that means just keep going like that. And so you could have that, and then you could, so if you had dot dot dot, and then this would say we do have an end. Dot dot dot, and then here's where it ends. But if it's just dot 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 and nothing else, then it just keeps going. Right. It just keeps going. Good question. Other questions? Okay, so actually these two were a web work problem, where part A was does the sequence converge, and what does it converge to? And then does the series converge, and what does it converge to? So let's take a look at those. So hopefully that sequence is pretty easy to see that it converges to what? Again, what are the terms in that? The terms are 2/7, 4/13, 6/19. Is that right? Okay, so that's what it means. But then there's another question, which I did not ask in the quiz, but it's important. Is this a convergent or divergent sequence? Do those terms get infinitely close to a particular real value, one particular real value? And you should all know immediately that it does it or not. Yes. What particular real value does it approach? 1/3. So we could write it this way. You could use limit, or you could say this. As the terms get closer and closer to 1/3, as close as you want. Take any small measure of tolerance. Eventually, the terms will get within that level of tolerance to 1/3 and always stay within it. Take a smaller level of tolerance. Eventually, the terms in the sequence will get within that tolerance and stay there forever. Okay, and you can keep making your tolerance smaller and smaller. That's what a convergent sequence means. Okay? I am, thank you. But just to be sure. Yes, I am, thank you. Okay. So then the question is, so basically then if we go out to say we keep going, and then we're going to go out to pick it up at the millionth term, say, the millionth term. When n is 1,000,000. The millionth term is going to be pretty dang close to what? Or say the trillionth term. The trillionth term in that sequence will be very close to what number? 1/3, right? When you make n big enough, the terms are just going to get closer and closer and closer to 1/3. So this symbol means like essentially 1/3. Essentially 1/3. Will it be exactly 1/3 at a trillion, n equals a trillion? No, but it'll be so close. It would take a lot of decimal places to distinguish between the actual term we get and 1/3. So this is for like n equals a trillion. Or how about 19 trillion? Some of you know why I picked that number. Okay, so n equals 19 trillion. Essentially, that term's going to be 1/3. And then they're going to get closer to 1/3. So basically, in the end, we just get 1/3, 1/3, 1/3, 1/3. Or so close, it's like indistinguishable. Okay, I'm making a big deal of this because of the series now. So what does it mean if we're going to add up? We're going to add up all the terms of this sequence. In the end, essentially, what are we doing? In the end, as n gets very large, we keep adding what? Okay, this is the most important fundamental idea of series right here. And then you're going to keep adding essentially 1/3. So it's not really exactly, but these are all essentially 1/3. Okay? And then getting even closer. Getting even closer. Is this going to converge or diverge? Is this series going to converge or diverge? Diverge. In the end, you just end up adding a number essentially equal to 1/3 over and over and over again. Clearly, it's going to diverge. You just keep adding 1/3 to it. It's just going to keep getting bigger and bigger. So if we have these sequences like this that are convergent sequences, how in the world is adding up all the terms of a convergent sequence, how is that going to converge to a finite value? How could a sequence that converges possibly add up all that, keep adding terms forever and get a finite value? How is that possible? Someone's got it up here. Anybody else? Yeah. Keep adding up terms that essentially are equal to 0. So in the end, it's like you're like not adding anything at all, over and over and over again. Now this has a chance, right? This has a chance to converge as a sum. But if you end up converging to something other than 0, again, this is the most important principle about series. This is the most important basic principle about series. If you converge to something other than 0, then what's going to happen in the end? You're just going to keep adding that value, or essentially that value, infinitely, and that can't possibly converge. Okay? The only chance is if your sequence does what? Converges to 0, because then in the end you're adding a bunch of numbers that are essentially 0, and now the sum has the chance to level off and actually equal a finite value. Okay, so this is what we call the divergence theorem for series. If the sequence converges to something other than 0, or if the sequence diverges, the series diverges. End of the story. If the sequence converges to something other than 0, or the sequence diverges, your series will diverge as well. Let's do that. Here we go. Let's write that out. Does the principle make sense before I erase what I wrote? Most important underlying idea about series. So here we go. Divergence theorem. Given a series, if the sequence, so I'll use limit notation this time. If the limit of the sequence is not 0, like we just saw the one, it was 1/3. It was 1/3. Or okay, and this has to make perfect sense in your brain, not something you memorize. If that sequence goes to something other than 0, just like the example we saw, then you're going to end up adding that value, essentially that value, over and over and over again, infinitely many times. That can't possibly converge to a finite value. Or if the sequence is divergent in the first place, that series will never converge either. Doesn't make sense. Okay, so now, what about this claim? If the sequence converges to 0, if the sequence does converge to 0, then the series converges. How about that? If the sequence converges to 0, then the series converges. What do you think? Yes? Let's take a look at this. So we're gonna now we're gonna investigate what's actually interesting. So this is kind of like, so what's interesting is when series converge. You're going to add an infinite number of things together and you're going to get a finite number, right? That's the interesting thing. So we get this out of the way. We say they can't possibly be convergent if if your sequence doesn't converge to 0 or is divergent. So now let's look at kind of the more interesting case of when does a series, when does adding an infinite number of things together actually give you a finite value? So certainly the sequence going to 0 is required, but is that sufficient? All right, so let's look at this series, the harmonic series. So the harmonic series is a very simple series of the sequence 1 over n. And so I was going to have you write out what it means, but it's already up there. But hopefully we bat 1,000 on that. Everyone would get that right. Right? So what does the harmonic series mean? It means 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. So in order to, the question, so does the sequence have a limit of 0? Does the sequence have a limit of 0? 1 over n. In the end, are we essentially adding 0 plus 0 plus 0 plus 0 for very, very large n? Yes or no? Yes. Is that enough to say that the series will add up to a finite value, will converge? That's the question we're investigating. So to investigate that, I want you to look at this series. So here's a series that kind of looks like the harmonic series, but it's a little different. So I want you to look at this second one. Is this second one have terms that are greater or less? Or is this sum going to sum up to something greater or less than the first one, the harmonic series? So talk to the person next to you. The second sum, is it greater or less than the previous? The second series. How many people think it's greater than the first one? How many people think less? Okay, good. The majority has it. So by making denominators bigger, you make a value smaller, right? So you have several denominators here that are larger than the one above. That will make your sum smaller. So I just put up a sum that's smaller than the harmonic series. Would you buy it? Because the denominators are at least the same or bigger than the corresponding denominators. So now look at this. In this new sum, this is 1/2. What's 1/4 plus 1/4? 1/2. What's 1/8 multiplied together 4 times? 1/2. What's 1/16 multiplied together or added together 8 times? So what I'm showing you in that second series is that as long as I take, so what will I do next? I'll take the next 16 terms, 1 over 32, and that will be 1/2. Will I ever run out of terms? I'll never run out. So I can always go far enough down the list and get a bunch of them to equal 1/2. And then I'll never run out of terms. Is this second series convergent or divergent? I can always go far enough out and get the next group to equal 1/2. And then if I go far enough out again, I can get another group that equals 1/2. Convergent or divergent?
Divergent.
Divergent. And how does this one compare to the harmonic series? What did we say? This one is what? Smaller than this one. or the harmonic series is greater than the one that we said is divergent. How about the harmonic series? Divergent or convergent? Divergent. Should make sense. We've got a series that's divergent, and the one we're looking at has a larger sum than that. Has a larger sum. So it's got to be divergent as well. So what question were we asking? If the sequence converges to 0, does that guarantee that the series will converge? That's the question we were asking. So does it guarantee it? Is it sufficient that the sequence is 0? Does it guarantee it? No, I just showed you one here. This 1 over n, that sequence converges to 0. The numbers get very, very as close as you want to 0. But if you add them all together, it still is an infinite value. Okay. You guys were discussing something back there. Are you guys good? Any questions back there? You're good? Okay. All right. So actually kind of two things happened here. We now found out that in order for a series to converge, the sequence has to go to 0. But is that enough? It's not enough, because not all sequences that go to 0 give you a convergent series. So we need something else besides that. Okay? And we've seen the principle before. The other thing that showed up here was what I used was called the comparison test. The comparison test. I had a divergent series, and then the series we were looking at had terms that were the same, at least the same or greater than the terms of the divergent series. And then we concluded that our series, 1 over n, was divergent. That's called the comparison test. Okay, so two very important things with this example. That sequences that go to 0 does not guarantee that the series converges, number one. And this idea of the comparison test. If you're analyzing a series, you can find a series whose terms are at least as big or bigger. No. Or less than, right? So if you can find another series whose terms are equal to or less than the terms of your series and it diverges, then yours has to diverge as well. Okay, so let's go back to the divergence theorem and summarize what we were talking about there. No, not a corollary. Just, So a follow-up comment to the divergent theorem. If the sequence converges to 0, then what can you say about the sum? Tell the person next to you. If the sequence converges to 0, what can you say about the sum of the terms of that sequence? What could you say? Go. All right, so if the sequence converges to 0, then the series converges, right? Is that what you said? Okay, we'll go with that, I guess. Right? Oh, you're shaking your head. Tell me. What did you say? May or may not converge. We just saw one that didn't converge, the harmonic series. So you should have said something like may or may not, depending on the sequence and the series. No conclusion about the series, unless, so if it's just generic like this. So you have each is case-by-case basis then. Case-by-case basis. We have to investigate the particular sequence and series that we have to figure out if that one converges or not. So it's necessary for the sequence to converge to 0, but not sufficient. Necessary, but not sufficient. Okay, so let's look at some that do converge. Okay, a geometric series. A geometric series is a special series of this form. A is a constant, some number, and R is also a number, some constant number. A, R to the n minus 1. So I want you to write, when you see that, what do you think? What does it mean? So, see that, think what? Write it down. See that, think what? Write it down. Okay, you should have wrote that. Did you write that? You should have. When n equals 1, you just get A. When n equals 2, you get A times R. When n equals 3, you get AR squared, etc. What kind of sequence is this kind of like? So we looked at some special forms of sequences. What kind of sequence is this kind of like? Remember? Yeah, the P. Remember the P to the n sequence. Remember that? P to the n. And when did that sequence converge? P to the n. So it's kind of like that, right? Because it's like, except we're going to start with 0, kind of. Like this would kind of be starting with n equals 0. But after this, it's the r to the n minus 1 is a lot like r to the n. It's basically like the sequence p to the n. And when did the p to the n converge? Greater than 1 or less than 1. When p is greater than 1 or less than 1, the sequence converges, right? Right? Greater than negative 1. Or between negative 1 and 1. So you guys got to have your brains on. You got to have your brains on. I'm saying that all of you did. But this converges when p is between negative 1 and 1. P is between negative 1 and 1. And what does it converge to, that sequence? 0. Okay, so this is worth talking about, right? If it converges to 0, then it makes sense to talk about a series converging that's kind of like that, right? If it converges to something else other than 0, divergence test means that the question's over. We don't have to talk about it, right? But if it converges, the sequence converges to 0, then we have something to talk about. When does the geometric series converge? Maybe it's the same conclusion. Maybe it's whenever r is between negative 1 and 1. Maybe. So let's investigate that. So yeah, so we want to know, when does it converge? For what values of r? A is just a fixed value. It's not going to play into whether it converges or not. So for what values of r does a geometric series converge? We want to investigate that. Okay, so what do we want to look at to do that? This is a proof, or kind of we're figuring out for what values of r does it converge. we want to look at what's called the sequence of partial sums. So we're going to make a sequence called Sn, and Sn is going to be to add up the first n terms. The first n terms. So it would be A plus AR plus AR squared. And we're going to keep doing that until we reach AR to the n minus 1. The first term is it's the A term. So this is the first n terms, and this is actually a sequence. The sequence goes like the next term in the sequence, you just add one more term of the series. And then the next term of the sequence, you add the next term. Okay? So this is the nth term of that sequence. And so I want to look at R times S of n. And you say, why do you do that? And I say, because it works. It works to do this. So what is R times Sn? Well, it's going to be R times all of the terms in the original sequence. I'm going to write the first. So A times R is AR. So I'm going to start here. And I'm going to line it up with that above. Okay, so plus AR squared. And then times R is going to be plus AR to the n. So I just took that sequence of partial sums, I multiplied it by R, and then I just moved them all over so that they lined up with the exact same terms lined up together. And so what I'm going to do now is I'm going to subtract. We got those all lined up. I'm going to subtract. What do I get? I'm going to get A. So I'm going to Sn minus R Sn equals A. All these are going to go away, right? That minus that, that minus that. They're all lined up. And then but we'll have this one, right? Minus AR to the n. Okay, and so then I'm going to solve for Sn. So Sn is 1 minus R. So there's just a lot of algebra, right? Just a lot of algebra. Arithmetic here. I'm going to solve for this sequence Sn, which is going to be A. I'm also going to, nope, I'm not going to do that. A minus A times R to the n over 1 minus R. And I'm going to split this up into two fractions. A over the denominator minus AR to the n over the denominator. So remember, this is like, what would we say? R to the n is a lot like what? P to the n, right? So what's going to make R to the n approach 0? Or as n gets large, become 0. So this whole thing is 0 as n goes to infinity if what? Think of it as the p to the n, right? P to the n. So, but now it's just r instead. If what? If r is between 1 and negative 1. So we're just using a new symbol instead of p. It's like r. And so as n goes to infinity, Sn, the sequence of partial sums, becomes that right there. So for what values of R does the geometric series converge? It's kind of what we thought, maybe, because we said that the sequence converges for R between negative 1 and 1, and that ends up also being how the series converges. As long as R is between negative 1 and 1, it converges. And what does it converge to? It converges to A over 1 minus R. So remember the turtle question. So real fast. Remember we did the turtle on Wednesday? And the turtle was 1 over 2 to the n. And that's actually one of these geometric series because it's 1/2 to the n. Starting at n equals 1. To make it like a geometric series, we need that to be n minus 1. So we can change it to n minus 1, but then we have one less 1/2 multiplied together. So we can pull the 1/2 out like this, and that's equal to that original series. So now here it is in geometric form. 1/2 times 1/2 to the n minus 1. And so now we can say, look, r is between -1 and 1, so this converges, right? R is between -1 and 1, that's our r value. And what does it converge to? A over 1 minus r. What is A? 1/2. So both A and R are 1/2. So A over 1 minus r equals 1/2 over 1 minus 1/2, which is 1/2 over 1/2, or, remember we said that the turtle, what? If you could add up all the terms, the turtle would make it across the backyard, and the sum was 1. So now we just showed it as a convergent geometric series. A over 1 minus r, 1/2 over 1 minus 1/2 equals 1. And that's just like the turtle example we did, but we reasoned it out kind of spatially last time. So now this is reasoning that same question using a geometric series. Okay, I went kind of fast at the end. Watch the video.